Yeah, good morning, everyone. I am Dr. B. Neelakanteshwar Rao, working as Associate Professor in Electrical Engineering Department of VNR VJIT. I'll be dealing with Power Systems 1 course. So let me first briefly introduce about this course. Power System 1 course is the basic power systems course in which we have different units. Like in the first unit, we'll be discussing about different means of generating electrical energy, like generating electrical energy from hydel power plant, generating electrical energy from thermal power plant, gas power plant, etc. And we'll also briefly discuss about how to generate electricity from renewable energy sources. And coming to the second unit, it basically focuses on transmission lines. And when we say transmission lines, these are basically made up of conducting material. So they do have a non-zero resistance, and apart from it, they also offer inductance and capacitance. So we in this unit will be discussing about the resistance calculation, inductance, and capacitance calculations. Apart from it, when we say transmission lines or transmission system, it is broadly classified into three types: short, medium, and long transmission lines. So we'll be discussing the detailed analysis about these lines in this unit. And in the next unit, we'll be discussing about the types of insulators which are used to connect these transmission lines to transmission towers. And also, we'll see some sort of sag calculations and tension calculations in the conductors in this unit. And apart from it, in the next unit, we'll be covering about the distribution system. That is how the distribution system is operate in a ring manner or in a distributed manner. These topics will be discussed in the next unit. So let me focus on today's topic, which is calculation of inductance. So how basically the inductance in transmission lines comes into picture. When a current flows in a conductor, surrounding it we have magnetic flux, and the ratio of flux linkage to the current flowing in the conductor is known as inductance offered by it. Now when we say magnetic flux, it can either flow inside the conductor or outside the conductor. So today we'll see the inductance calculation due to flux which is internal to the conductor. We call this flux as internal flux. So let us see about it today. So as I said, today we'll be seeing calculation of inductance due to internal flux. Now let us consider a long cylindrical conductor of unit length. So I have already predefinedly drawn some figures. I'll be making use of those figures to make you people understand the inductance calculation due to internal flux. So this is a conductor whose length is say 1 meters. Now this second figure shows the cross-sectional view of this conductor. Let small r be the radius of the conductor, and let capital I be the current flowing through this conductor. Now, according to Ampere's law, we have the MMF around the closed path of this flux is equal to the current enclosed by this path. So this is mathematically expressed as integral of H ds. So this will be equal to capital I, which is the current flowing through the conductor. Now in this expression, capital H represents the magnetic field intensity and small s represents it is the distance along the closed path. Or distance along the flux path rather. And capital I is the current which is flowing in the conductor. And as we know, H is the magnetic field intensity. H is given by Ni by L, where N is the number of turns and I is the current and L is the length of the conductor. So the units of this magnetic field intensity can be taken as ampere turns per meter. Similarly, the distance can be measured in meters and the current can be measured in amperes, right? So here, now if I take a portion or a point on the conductor which is at x units from the center of the conductor. So here what I am doing is I am taking the same conductor which is at x units from the center of the conductor. So this point I am taking as x, which is concentric in nature. And if I say Hx is the magnetic field intensity, at this point x, and say the amount of current enclosed in this portion whose radius is x as Ix. So Ix is the current enclosed in the portion of conductor which is represented by this dotted line. Then I can write, according to Ampere's law, integral of Hx ds will be equal to Ix. Now this can also be written as I am taking the closed surface along the path whose center is at a distance x units. So then this becomes 2 pi x into Hx. This will be equal to Ix. This implies Hx is equal to Ix by 2 pi x. Right? So let this be, let us give some equation number to this. So already we have given equation number 1. So let this be equation 2. Now, assuming uniform current density throughout the conductor, we can write the total current flowing in the conductor to the area of it, which is pi r square, will be equal to the current Ix, which is flowing in the portion of the conductor, to pi x square. It implies Ix by I is equal to pi into x square by pi into r square. So this implies, so pi in numerator and pi in denominator get cancelled, from which we get Ix is equal to x square by r square into I. Let this be equation number 3. Now, substituting equation 3 in equation 2. So, from equations 2 and 3, we get Hx is equal to, now I'll substitute Ix is equal to x square by r square into I in place of Ix in equation 2. Then this becomes x square by r square into 1 by 2 pi x into I. So here 1x in the numerator and x in the denominator get cancelled. So this becomes x by 2 pi r square into I. This is equation 4. Let this be equation 4. Right. Now, if I want the magnetic flux density at point x from the center of the conductor, that can be expressed as Bx, where B is the magnetic flux density at x meters from the center of the conductor, is equal to mu into Hx, right? Let where this mu represents permeability of the conductor. Now, if I want to calculate flux at that point, what I basically do is I just take a tubular element at this point x. So what I do is I just take this tubular element which is at x meters from the center of the conductor. So this is x. So this distance is dx basically. Right. So why we consider this tubular element is we are considering basically a small length at which the magnetic flux density is same, that is the magnetic flux density at this point x is same as that of x plus dx, and the current enclosed is also almost same between this point. So that is the reason why we are considering this small tubular element whose width is dx. Now in this tubular element, if I want to find the flux, so flux in the tubular element will be equal to the product of this magnetic flux density Bx and the area of the area which is normal to this flux lines. So now let us see how to find the area which is normal to the flux lines. So here I have taken I have basically taken a cylindrical shape of this conductor. As I said, the length of this conductor, what we are taking is 1 meters. So as I mentioned earlier, now from the center of the conductor, this is the side view of the conductor, which I have tilted slightly to give you a picture of how the flux lines or the path of flux lines exist. So this point is from distance x from the center of the conductor. Now here I have directly taken the side view without tilting in the second figure. Here what you can see on this screen. So this length will also be same, which is 1 meter, but this view is exactly the side view. Now if I assume the current to flow from right to left in this manner, if I take this as the current direction, now if I apply thumb rule, now the current in this top portion will enter into the flux in this top portion will enter into the conductor, and in this bottom portion it will leave the conductor. So to have a feel, I have taken this cross and dot notation so that you can have a feel of the flux which is entering in the top portion in the tubular element, whose width is, as we have taken, this is dx. This width is dx. So in this top tubular element portion, the flux is entering, and in this bottom portion, it is coming out. Now, as I said, if I want to calculate the flux, that is nothing but it is equal to the magnetic flux density at that point multiplied by the area which is normal to the flux lines. Now, what is this area which is normal to the flux lines? That is equal to the width of this tubular element, which is equal to dx, multiplied by the length of the conductor, which is 1 meters. So this ultimately comes to be bx into dx, which is the width of this tubular element. Now let the flux in this tubular element be d phi. Right. So now here we know that flux as generally the units as Webers, but since we are considering a conductor of unit length of 1 meter, this differential flux d phi will have a unit of Weber per meter. Now if I want to calculate the flux linkage in this tubular element, we generally use lambda to represent flux linkage. So I am using d lambda to represent the flux linkage in the tubular element. So that will be equal to the flux in the tubular element multiplied by the fraction of current which is linked by this flux d phi. So when I is the total current and Ix is the current which is flowing in this portion, Ix is the current which is flowing in the portion between the center of the conductor to the point X. So here we can write the fraction of current as Ix divided by I. So Ix by I basically represents the fraction of current which is linked by the flux in the tubular element. Alright. So already we have from equation 3, we have Ix by I as x square by r square. So here you can see from equation 3, you have Ix is equal to x square by r square into I, from which Ix by I will be x square by r square. So that is what I have written here, right? So now the next equation number we can give it as phi. This will be equation 5. Or let us take the earlier equation as phi and this equation is 6. Now substituting equation 5 in equation 6, we get d lambda is equal to, in place of d phi, now we may substitute bx into dx. So bx into dx into x square by r square, or I can also write this as d lambda is equal to bx into x square by r square into dx. Let this be equation 7. Now already we have derived an expression for bx. If you see equation 4 and the expression for bx is equal to mu into hx. So we may write this equation 7 back again as d lambda is equal to mu into hx into x square by r square, or x by r whole square into dx. So that will be equal to again mu into, from equation 4 we may write hx is equal to x by 2 pi r square into I. So it is x by 2 pi r square into I into x by r whole square into dx. This implies d lambda is equal to, now I can rewrite this expression as mu I by 2 pi r power 4. Why? Because r square already it is in denominator, and we have got one more r square in this parenthesis part, so it becomes 2 pi r power 4 into, in numerator there are totally 3 x terms multiplied. So this can be written as x cube into dx. Let this be equation 8. Now if I want the total internal flux linkages, so when I say total internal flux linkages, they are the flux linkages from the center of the conductor to the surface of it. I'll represent it as lambda int. Then this can be found by integrating the flux linkages in the tubular element from the center of the conductor to the surface of it, which is at radius r units from the center of the conductor. So I'll just substitute the value of d lambda in this integration. Then it becomes mu I by 2 pi r power 4 into x cube dx. Mu I by 2 pi r power 4 is a constant with respect to x. So I'll take it outside. Now rest part of the equation will be 0 to r x cube dx. So it implies lambda internal will be equal to mu I by 2 pi r power 4 into integration of x cube with respect to dx is x power 4 by 4 with lower and upper limits as 0 and r. So if you substitute the limits, you will be getting mu I by, now already you have 4 in the denominator and apart from 2, so this will be 2 into 4 or 2 into 4 into pi into r power 4, and when you substitute the limits in numerator you get r power 4. So r power 4 and r power 4 in numerator and denominator get cancelled. So this becomes mu I by 8 pi. So let this be equation 9. Now this permeability mu can be expressed as the product of permeability of free space mu naught and the relative permeability, where mu naught, as I said, is a permeability of free space whose value is 4 pi into 10 power minus 7, and the value of mu r, the material which we are considering is a non-magnetic material for which the relative permeability is approximately equal to 1. So substituting these values in mu, we get mu is equal to 4 pi into 10 power minus 7 for overhead transmission line. Now substituting this value of mu in equation 9, we get, so from equations 9 and 10, we get lambda internal is equal to 4 pi into 10 power minus 7 into I divided by 8 pi. So which is half into 10 power minus 7 into I. Right. So and so Weber turns per meter. Now, if I want inductance due to internal flux, or internal flux linkages, that can be found as L is equal to lambda by I. So from above equation, if this equation is say equation 11, from this above equation we can write lambda internal by I is equal to half into 10 power minus 7. So actually the inductance unit is Henry, but since we are considering a unit length conductor, so the unit of inductance due to internal flux linkages in this derivation will be Henry per meter. Let this be equation 12. So from this equation you can see that the inductance which is calculated due to internal flux linkages is always a constant whose value is half into 10 power minus 7 or 0.5 into 10 power minus 7 Henry per meter. In the next session, we will be seeing how to calculate the inductance of a conductor due to external flux linkages. Thank you for today.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.